So far, in the discussion of hill slopes, we've really just talked about hill slope diffusion, so the gradual creep of material down the sides of the slope. However, that's not always the way that hill slopes evolve and fail, or, fail was really the operative word there, evolve and move material. Hill slopes can also move material in sudden failures that we call mass wasting events. And so mass wasting events include landslides and many other types of sudden failures. And when we're trying to understand mass wasting events, what we do is we actually turn to a tool that we have called Continuum Mechanics. And so Continuum Mechanics is, if you imagine like your classic physics problem in an introductory physics class, you're always considering what's happening on a rigid body. Inside Continuum Mechanics, we think about what happens when that rigid body starts to deform internally. And more specifically, I'm going to consider brittle failure of that body. So I'm not really concerned so much with flows, things that you might see in water. What I'm concerned about is what happens when you have something that is solid and then suddenly slips and fails. And so this sort of approach is used to understand faults in the earth, fractures in buildings, used to understand, the stability of aircraft and so forth. It's really commonly used in engineering. And it's also something that we can use to understand landslides. So if we have a certain stress that's applied, and so I'm going to say that there's sigma, this is a stress, that's applied to a body, there's going to be a set of responses to that inside that body. But first off, let's just define a stress. So a stress is a force per unit area. And so that if I create something like this, where I have this area, and I have some sort of, set of force vectors, so all of these vectors together, but if I just look at, some sort of single one, maybe I'll even change the color, that might help. So if I'm just kind of focusing on one single one right here, and perhaps on just like one single cross section in this plane, then this is going to be the stress, which is going to be force per area. And the reason I want to do this is because this is what really matters, right? So if I have a ton of force, but spread over an area that's, a kilometer wide by another kilometer long, then maybe the actual stress in every individual piece there is going to be pretty small, and that won't matter so much. So what I want to do is figure out, on the other hand, right, if you have, like, if you're jumping up and down on the edge of a cliff, or if you're like, driving a gigantic truck to the edge of the cliff, then maybe you're actually loading that piece, that local area, a lot more, and maybe that is what's more likely to cause, a large amount of stress on that edge. And it's stress that's going to cause the failure of the surface. So before we go too far into the mathematics and the physics, I just want to show you some pictures of landslides. This is from a figure I got online. It's made by somebody. I don't actually know the copyright. I looked hard and wasn't able to find it. So if this is yours, please let me know. But there are a number of different mechanisms by which these landslides can fail. One of them, here I'm going to use red for this failure color. So one of them is having a scarp that causes a rotational failure like this, and that's because we have this free surface up here. And so, if this fault were to continue going straight down there, it would just go deeper and deeper into the earth, and then nothing would move, right? It's going to hit this point at which there's, you're just deep in the bedrock. And so in order for this material to move, this fault surface ends up scooping up towards the Earth's surface and creating a rotational landslide. Of course, and there can be other cases in which if the hill slope is looking, like this, where it has a steeper slope than the landslide scarp itself, then we can have a rupture here, which then daylights at the surface right there. And so that creates a simple planar failure, and that is a translational landslide. So this block just goes straight downhill as opposed to this one, which is, moving out and back up again. We can have something that's called a block slide. So there's a surface rupture here, and then this material just scoots along that particular surface. And in this case, what you're seeing is that there's some sort of cliff here, and this escarpment, and this material is fallen down into that valley. Rockfall is something like this, and so what you can see is that these rock units are already dipping this way, right? And there would have been something, you know, right along here, and it would have been connected here by fractures. And it already has a preferentially aligned plane of weakness with a point at which, or in fact even a plane at which it can detach. And so because of that, it ends up being actually quite easy for this rockfall to just, you know, plop from there down to there. We can also have a landslide that's called Topple. Some of my colleagues like to call this the face plant, and then they call the rotational landslide or the translational landslide the butt slide approach. But this Topple landslide means that we're not just talking about some sort of like force balance on this, we're actually talking about a torque balance where this is rotating out, and so there's some sort of torque involved. There are also debris flows, and so what this is that there is some sort of landslide event up here. I'll just write LS for landslide. And then that triggers an overloaded slurry of like mud and water and boulders and debris. That then flows out of the mountains or out of some high upland area. So these debris flows can occur on land. They can also occur underwater in the oceans. And the key here is that unlike a river, which has a relatively low concentration of sediment in the water, these debris flows are laden by so much sediment that it actually changes the viscosity and the physical characteristics of the flow itself. There's also this one over here, which is this debris avalanche. Oh boy. This debris avalanche. And you can see here, everything is just this big jumbled mess that's, you know, coming off of this initial scarp. There's an earth flow here where everything has sort of become liquid, and so you can see that this actually looks kind of like you'd expect if you had a bunch of honey or molasses on the side of a table just creating this, flowing down and creating this big lobe. And so this is more, you know, more liquid. And those can occur with liquefied muds. They can also occur at some points if there's something like, you know, melting permafrost. So again, liquefied mud. Over here, this is what we've been talking about for the longest time, is hill slope creep. And so you can see that you might expect these curved tree trunks. If you saw the virtual field trip, you'll be familiar with that. You might have some tilted poles or fences out of alignment as this material just all slowly and at different rates creeps down the hillside. And then there's also some amount of lateral spread that's possible. So let's see, if we have something like a river valley here, then this is creating a free surface. So in that case, you know, if there's something in the middle here, there's, you know, this block is supporting this block over here, but over here, you know, unless you're actually here like pushing on it as a person, there is nothing actually holding this side up, so material can kind of spread out to this side laterally. And so typically when we're looking at these stresses, we use sigma as a term for the normal stress, which contributes to friction and is perpendicular to the plane of failure. And we use tau for the shear stress, which is parallel to the plane of failure and drives motion. Someday I'll be able to underline on this tablet, okay. To be honest, I'm also not very good at underlining, even with a pencil and a piece of paper. So what I want to do is go through like how we set up an equation to understand failure within a continuum. And to do so, I'm going to actually go back to introductory physics and show you this free body diagram. And then after this, we're going to go into how we translate this into stresses. So first off, what we're doing here is we can think of this more like one of these translational failures. And if I go back up here, so we're thinking about this translational landslide, something like that right there, where we just have some sort of block that's moving down a plane. And so the way this all works out, and this figure is just borrowed from Wikipedia. Thank you, Mets501. Wonder if you're from New York. And so there's a normal force, which is directed out this way from this, and the normal force times the coefficient of friction is equal to the resisting forces. Meanwhile, the driving forces are defined by this mass times gravity, which is the weight of that block, times the sine of this angle theta. The normal force is mass times gravity times the cosine of the angle theta. And so what we have is a simple kind of set of equations where we just have to balance the driving and resisting forces. So driving is going to be mg sine theta. Resisting is going to be this coefficient of friction times mg cos theta. And from this, we can see that at incipient failure, we can say that the driving forces, mg sine theta, are going to equal the resisting forces, so friction times mg cos theta. And because we have mg on both sides, actually the mass of the block cancels out. And so then we can find from this, based on this coefficient of friction, F here, what the actual angle of failure should be. And so one thing I just want to let you know is that F equals mu for much of what we're doing here. So this is just coefficient of friction. Just in geology, we just use mu for coefficient of friction quite frequently. We use it also for dynamic viscosity. We just don't have enough Greek letters. That's the fundamental problem in trying to derive these equations. And so then if we want to then, let's just replace that and we can say sine theta is equal to mu cos theta. Didn't leave myself quite enough room. Then what we can say is that mu is equal to sine theta over cosine theta, which is equal to tan theta. And so therefore theta is equal to tan inverse or arctan of mu. And so then we have this is the coefficient of friction, and what we can call this is the angle of internal friction. And you might be wondering why I said internal, because this is actually external in this example. So I'm going to scroll down to this next figure. And so if we have a continuum here, if we have some sort of block through here, on the top of this continuum we have some amount of material pressing downwards, right? And so this is creating some sort of stress. And that's just going to be, I'm just going to write this stress here as basically just a mass times a gravitational acceleration over this area. So we have essentially mg, right? So that's going to be the force over some sort of area on this plane. And this is going to be kind of cartoonish. I'm not going to be trying to solve everything, but I'm just trying to show you what's happening in pictorial form. And what that does is it creates this stress that I'm going to call sigma. And in particular, we think of sigma as, in this case, as the normal stress. So we have sigma going out like that. Let me just rewrite this here. So we have sigma, which is this normal stress. And then we have another stress over here. I'm going to draw that in red because it's driving the failure. And that stress is going to be tau, which is the shear stress. And let's see if I did everything I was supposed to. Angle from the horizontal as well as the orientations of the normal stress and the shear stress. So we have the normal stress there, the shear stress there, and then of course the angle from the horizontal. That's just going to be right here. And that I will often refer to as alpha, sometimes I'll refer to it as theta, but that's the angle that's driving this failure. And so the next step that we have to go through is to just see how this particular setup of stresses compares to the basic force balance on inclined plane, and how we can go from there to then understanding whether or not a hill slip will be stable and whether a landslide is likely. And we're going to go through that next time.